Today, it's light, color, and rainbows, and we're gonna do 2 demonstrations and an art project to get our minds wrapped around this very cool thing called light. And I think with that, we're ready to go. And again, hello to all of our families at home, in kitchens, and in living rooms. Hello to all our virtual teachers in classrooms. And hello, if you are on YouTube, it's the theme song portion of the event. Welcome back. Welcome to the ROMKids Show with me. We'll do some crafts and tell some stories. Let's talk about science, art, and history. Welcome to the ROMKids Show, starring you and me. There we go. That's the theme song portion of the event. As you look around our household, you will see that the set looks a little bit different, and by set I mean living room, and it's very much because we are in the process of moving, so like kind of exciting, but also kind of messy, kind of chaotic, but we still want to do the show with you. And next week we're going to be doing the show with you from a different location, which we are very excited about. Okay, so today, light, color, rainbows. Very excited to do this. We're gonna do 3 different demonstrations, but before I tell you what you need to get, all right, let's welcome to the show, and as a big return, Julie Tomé. What's going on?
Hi.
Oh, this is so.
Thanks for having me again.
Oh yeah, up on YouTube you can find episodes about constellations. You can find episodes. Well, we talked about the moon. We talked about something else too. We talk about a lot of stuff with Julie Tomé, and she's one of our favorite guests. We are talking about light today. I love that rainbow behind you. Before we get started, here are the things that you're going to need. So for our first project together, for our first demonstration about light and light refraction, you need paper, you need a marker or pencils or anything to color something with. And then you need a glass of water, and that is it, all right? For the second project we're doing, you need a glass of water, some milk, and then I have a 1/8 teaspoon, so something that you can dab milk into your water very, very slowly. And then our third project our second project's all about why the sky is blue. So if you have questions about light and sky and why things are the colors the way they are, drop them in the chat. And then our final one is a rainbow, candy rainbow. And you need either like Smarties or M&Ms or Skittles, water, a plate, and a brush, okay? So those are the things you need. Start considering what you need to get. For our first one, you need paper, coloring materials, and a glass of water. My first question, Julie Tomé, what is light?
All right. Well, that's kind of a tricky question to answer because most people think of light as a wave, and it is a wave, but it also has this weird property called particle wave duality, which means sometimes it acts like a particle, like an itty bitty little tiny ball. But we'll be focusing more on its wave behavior today.
Okay, I like that. So let's do our first step for our project, okay? For our first demonstration, what I want you to do with a piece of paper that will fit behind your glass, okay? I want you to draw anything you want as long as there is an arrow. So you can draw a person with an arrow. It could be a monster truck with an arrow on it. It could be a dinosaur with an arrow. Just has to have an arrow pointing in one direction, and then the rest of the drawing is up to you, and it just has to fit behind your glass of water. So I want you to work on that. Light is complicated like so many things. Let's try and go a little bit easier here. Where does light come from?
All right. Well, a few different places. My favorite source of light is the sun. And in the sun, there are little tiny things called atoms, and there are different kinds of atoms. And they come together, they're moving around super fast, and every now and then they smash into one another. And they stick together and make a new kind of atom. And when they stick together, that releases a whole bunch of energy. And we see that energy as light, and we feel that energy as heat coming from the sun. And there's similar reactions. It's basically changing energy from one form to another form. So could be friction turning into light. It could be other things. It's just energy changing from one form of energy into light.
Yeah, this is really exciting. We were talking before the show how like light is in some ways more complicated to talk about than even like big societal issues like water equity. But we're coming at you with physics today on the ROMKids Show. So get ready for that. Okay, something that I've been meaning to ask, and I don't quite understand it because I hear it a lot, and maybe you've heard it at home too, is what does it mean to travel at the speed of light?
All right. Well, light has a speed because it starts, for example, it starts at the sun and then it travels all directions in our solar system and eventually gets to the Earth, right? And it doesn't get there instantaneously. It does, like if you were traveling, say if I were traveling from my home here in Aurora to the museum, it's not like, boom, I'm there. It takes me about 45 minutes if the traffic is good, right? And I'm going about 100 kilometers an hour. Well, light travels at 300,000 kilometers per second.
What? That's so fast.
So that's what it means to go at the speed of light. And as far as we know, that is the universal speed limit. Things cannot go faster than light.
Whoa. Okay, so if I'm thinking about this correctly, that means when I see a star and I see the light that it's given off, by the time I see that light happened a long, long time ago.
Yeah. So depending how far that star is, so the closest star other than the sun let's start with the sun because the sun's important. The sun is our closest star and it takes about 8 minutes from the light leaving the surface of the sun to reach our planet. The next closest star to us is Proxima Centauri, and it's 3 or 4 light years away. I think it's 4 light years away. So when you see that star in the sky, you're looking at light that's 4 years old.
That's
and
awesome.
All the other stars are even further out. So that some people say that telescopes are time machines because you're looking at the star like it was however many tens or hundreds of years ago, or 3 or 4 years ago for things that are closer.
Okay, so that means because stars exist, they form, they combust at the end in a supernova. That means that we can be seeing light in the night sky that doesn't exist anymore. Like that star has already disappeared.
Yeah, so for example, a lot of people pay a lot of attention to the star Betelgeuse, and it's about 500 light years away. So if tomorrow we saw Betelgeuse go supernova, well, that actually happened 500 years ago. We're just getting the news now.
That's awesome. That's awesome. I didn't even think we'd go that deep on this sort of niche part of the show, but the concept of time and travel and light all coming together is fascinating. Okay, going a little bit closer back to our story about light, you can see here I drew a dinosaur. As you know, my favorite thing in the world is dinosaurs, followed by tacos. So I got my dinosaur right here holding an arrow sign. So JT, we're going to talk about light refraction. What does that mean? And I'm just holding up to our camera right here a cup of water and a straw. And I'm not sure if our viewers at home can see it, but I can see the straws don't line up. What is happening there?
Okay, so light travels in straight lines. But when it meets a surface so right now, most of the light you're traveling through air. And then it gets to your glass. So there's air and there's glass. And when it gets to that surface, its speed changes just a little bit. And that causes it to bend. And then the light goes through the water and the glass. It bends when it gets to the glass and the water. It bends when it gets to the other side of the water and the glass. It bends when it gets to the glass and the air. And then it comes out the other side. And you're seeing the light has been bent a whole bunch of times. So that straight straw now looks a little bit weird.
Huh. Okay, so we're going to do another demonstration here. which I think shows light refraction in a really cool way. So what I'm going to do is I have an empty cup right here. I'm going to hold up my dinosaur right there, and you can see the arrow is pointing to my left, right? You can see that. It's pointing to my left. Now I'm going to take some water and I'm going to fill this cup up. Did it flip? Did it not flip? Come on, light refraction. This is science.
Maybe move it a little bit back from the glass.
What about now? Okay, let's try this one. There we go. So we needed a nice big image for it to flip right there. That was interesting. Physics. But you can see how my arrow has flipped this way. It's pointing this way. Oh, I gotta put it farther back for it to work. Wow, JT, we're doing physics in a real way on this show right now. So my arrow is really facing left, but as you can see it, it's actually going right. What is happening, JT?
All right, so that's some physics with the light bending, but it's also a little bit of geometry as well. So you can imagine when the reason we see what's on the paper is light is bouncing off the paper and into our eyes. And because we are looking at it through a glass of water, well, those rays, think of a ray coming from the back of the arrow, a ray coming from the front of the arrow, they're getting bent and they're crossing, and then you see them, but the ray that was at the front is at the back, and the one that was at the back is at, well, it looks like it flipped, right?
Yeah.
So the one that was left is on the right, and the one that was right is on the left, if that makes sense.
Mm-hmm. This is kind of like how our eyes work too, and how the light bounces around inside. Light is wild. We want to talk about color, okay? So this next demonstration, because we're all building up to get to rainbows right here, okay? So our next demonstration, you need a cup of water, okay? And go get yourself some milk. We have skim milk here, that works. I'm sure 2% and 4% and those ones work as well. I'd be interested to know if almond milk works or cashew milk works. But grab those materials. JT, how are colors made?
All right, well, colors are different lengths of waves in light. So when we're looking at white light, that's all the colors smashed together. But a red wave is a little bit of a more stretched out wave than the purple. Purple is a little bit more squished. And so when you're looking at that wave, it's got bumps in it and it's got dips in it. And when you look at the distance between two bumps, that's called a wavelength. And that's the wavelength determines the color. So if you have a longer wavelength, then you're looking at something more red, and a shorter wavelength, you're looking at something more purple.
Oh, you can see it here. So see how the red wave is longer and the purple wave is shorter? And so that's how you get colors. That's awesome. Sorry, I'm just showing that cool GIF I was showing you earlier.
Yeah, that one's really cool. And it's showing it going through a prism, right?
Yeah.
So the different wavelengths will bend a different amount. So the red will bend the least and the purple will bend the most.
Okay, I think this might be almost a philosophical question, but why are there different colors? Is it just that the waves of the light and that's it?
Yeah.
That's it. It's just the way the light bends. Okay, so a question that we get a lot as educators, and certainly I asked a lot as a kid, is why is the sky blue? Why is the sky the way it is? Why is it blue? And today in Toronto, it's a beautiful blue sky with some clouds. Why is it blue? Should we do the demonstration and then you can talk about it, JT?
Yeah, let's do it.
Okay, so we got our cup of water right here, and then I'm using my 1/8 teaspoon right here. So I'm just gonna, you can also use like an eyedropper or something like that to slowly drop your milk into your cup. Okay, so I'm just getting that milk, and then I'm dropping it in. And you can see how, oh, I need a flashlight for this. Sorry, you need a flashlight, everyone. Good thing for me to remember that, because otherwise this activity wouldn't have worked. So, I have my flashlight right underneath, and you can see how it's a little bit bluish, okay? It's a little bit faded. It's a little bit wispy like the day sky, as opposed to originally when the light is just white, okay? And that's something I want you to try out. Put your light underneath your water first without putting anything in it and see what color it looks like. Then once you add your milk in, how does it change? So JT, what's happening here?
Okay, so what's happening here is something called scattering of the light. And if we want to get fancy, it's Rayleigh scattering. So in our atmosphere is that thin layer of gases that's all around our planet, super important, protects us from UV rays from the sun, and it gives us something to breathe, very important. And it's made up of a specific mixture of gases, mostly nitrogen and oxygen. And those are all little molecules, or little tiny bits all in this area moving around. And when the light from the sun comes into our atmosphere, the molecules are just the right size to make the blue light go boing, 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 all over the place. So a photon, a particle of light, will hit one of these molecules in the atmosphere, and it'll bounce off in a direction. The next one will bounce off in another direction, and there's no rhyme or reason to the direction it's going. It's going all over the place. So when we look up at the sky, we've got blue light coming at us from everywhere because of this scattering, and it looks like the sky is blue.
So I'm adding in some more milk, and already I'm starting to see it change a little bit, change into more of an orangey color. I'm gonna add in a little bit more. I'm wondering, JT, is this what happens when it's like a sunset or a sunrise? Whoa, look at that, it's like orange. Can you see that? I'm gonna put some more milk in.
Yeah, so at sunset and at sunrise, you're looking at the sun through more of the atmosphere. So when it's the middle of the day, the sun is right above your head. It's got, say, this much atmosphere, but when it's sunset, the light is coming through way more atmosphere. And so it looks orange or reddish because all the blue light has been scattered out of that ray of light when it gets to your eye.
So there's more atmosphere that the sun is going through at sunset and sunrise, and that's why we get those gorgeous colors. And then there's less atmosphere that the light is going through during like the proper day because there's less atmosphere above us, and so that's why it's blue.
Yeah, so the atmosphere is a regular, like it's got a regular thickness all around the Earth. It has to do with the geometry, right? During the day, the light's coming at you more from above, and then in the evening, it's coming at you from a shallow angle, right?
Oh, got it. So the angles are really important, and then the angles and how it interacts with those particles. That's really cool. We really like that experiment, and I tried it for the first time this morning, and it was super, super cool. Okay, I have another question that comes up a lot. Why are leaves and so much plant life green?
All right. Well, leaves have something called chlorophyll in them. And that's an important thing in the leaves. It helps plants do photosynthesis, right? They take the sunlight and water and carbon dioxide, and there's a chemical reaction that happens, and it makes food for them as well as oxygen, which is really cool for us since we need that to live. And that chlorophyll is green. So what we have there is something called subtractive color mixing as opposed to additive color mixing. And so what those leaves do is they absorb all the other colors of light that are hitting it and reflect the green. So that's why we see them as green. All the other colors are being absorbed into the leaf, and the rest are being bounced back to our eyes, the green.
Oh, okay. We did not talk about this beforehand, but I'm thinking we can probably pull this one off. Because we just talked about blue and we talked about green and how it's reflecting back the green. What is white? Why is white the shade or color that it is, and why is black the shade or color that it is?
Okay, so now we're talking about additive color mixing. So you take all the colors of light that we can see, you put all those waves stack up and it turns white. Black, then we're going back to subtractive. So when you go outside, so I'm wearing a black top today, right? If I were to go outside in the sun, it would feel really hot in this top. If I were to go change into a white top and go into the sun, I wouldn't feel as hot because black things absorb all that light. They don't bounce that light back. And that's why we see black, which is an absence of color.
I like all that. So, it's starting to warm up here in Toronto. Looking forward to seeing everyone in beautiful white clothing to stay cool. All right, obviously the main event for why we're here today is rainbows. So, I'm pulling up a plate right here. I've already neatly organized it. Oh, this is a great time to talk about Roy G. Biv. This is important for us. So what I want you to do is I want you to grab yourself a plate. I want you to grab Smarties, Skittles, or M&Ms, or any similar type candy. I want you to make a circle with them in any pattern you want. Now, the pattern I chose is based off of Roy G. Biv, which is a clever way to remember something. What does Roy G. Biv mean, JT?
It is the order of the colors in a rainbow. So red, orange, yellow, Roy. G, green. Biv is blue, indigo, violet. Now, we don't talk about indigo a lot, but it's a color that's not quite blue and not quite purple. Kind of in the middle.
I like that. And here you can see the bottom of a rainbow right there. You can see Roy G. Biv played out. So with the colors that I had in my M&M collection, which I've held on to since Halloween, I have red.
Wow.
Yeah, I know, it survived. I got the Roy right here, right? So I got R for red, O for orange, and Y for yellow, so Roy. Then I got the G in green, and then I have the B for blue. And then I don't have Roy G. Biv, so indigo or violet. So those are just, you know what, M&Ms, make those colors. I need it for this experiment. Please do so. This is a request. Okay, so that's the way that I've arranged my M&Ms here. You can arrange your candy in any which way. So take a minute to do that, and let's talk about rainbows, JT. What is a rainbow?
All right. So we've talked about refraction of light. We've talked about scattering of light. Now we're going to talk about reflection of light. So you showed that picture that showed the lights, the different colors being spread by the prism. So when a ray of light enters the droplet of water, it's going to first do that spread, red at the top, purple at the bottom. And then if you picture a droplet of water, the light's coming in, it's going to bounce off the back. It's going to reflect, most of it is going to reflect off the back. And then it's going to exit the other side. And so what we get then is a rainbow, all the colors separated, red down to purple.
That's so cool. Okay, I have a question. Why are they like arched? What's the deal with that? Like we're showing one right here, and it's like this perfect arch. Why is it that way?
Well, because it has to do with angles. So it's going to be between 40 degrees and 42 degrees. What does that mean? So a full circle has 360 degrees in it. So 40 degrees is about, I guess, an eighth of a circle-ish, right? Mm-hmm. And so it all depends on where you're looking, right? So it's 40 degrees up, 40 degrees to the side, 40 degrees over there. So that makes a nice circle.
There you go. We did not prepare to talk about math today. At least I was not mentally prepared to talk about math today. But it is certainly very important when it comes to physics, light, and rainbows. Okay, so now I'm going to take my water and I'm just going to pour gently into the center, okay? Just enough so that it covers right at the bottom of our plate, all right? And let's see what happens. I hope I have enough water here. If I don't, luckily enough, I have more water. Because I do come prepared sometimes. And so I'm just trying to fill up that bottom space so that it covers all the base of our M&Ms. And like, let's watch and see what happens. This is water soluble. which means that the ink in the M&Ms interacts with the water and the water pulls it away. And you can see just how fast our rainbow is forming. JT, I don't know if you can see it, but it actually looks cool. That's awesome.
That is really cool.
And so this is our candy rainbow. Something that we hear a lot, or at least is in the pop culture, is a double rainbow. What is that?
Mm-hmm. Okay, so with a double rainbow, you're actually getting, so in the main rainbow, you've got one reflection in that droplet of water, or it's actually a whole bunch of droplets of water. And then with the double rainbow, you're getting a double reflection. So it's coming in at such an angle that it would say maybe bounce off the top, bounce closer to the bottom, and then back out. And because you're getting that double reflection, you're actually getting the colors inverted. So instead of Roy G. Biv, you have Vib G. Yor?
Yor? I think so.
Vib G. Yor.
That's funny. Okay. Now, what you can do with this beautiful mixture, and I love the way that this is turning out, and the red and the purple or blue are sort of making a purple in there, so sort of representing violet.
So you're getting the IV in there.
Yeah. So take a brush, and you can now use these inks to paint. All right, and I'm just going to do a simple I'm just going to take some of that R. I'm going to take some of that red right here. And I'm going to build a nice little R. I'm going to take some of that blue, because you can paint with this, friends. Honestly, this water might taste pretty good too. I'm going to take some green for an M. But what I really want to show you is that you can have these, see, like slow, it's a watercolor. It's a very light watercolor. You can see the one that I made over the weekend right there. So you can paint with this, and I sort of like just how soft and light it is. Now, if you have a skewer, you can also make some designs and mix these colors up. So I'm just going to draw a little circle in the middle, and you can see how the colors start to interact with each other. Another circle. To me, it kind of looks like a nebula in space or something. And you can see these really sort of like beautiful swirls start to form, which sort of reminds me of like almost the formation of the universe. Or a rainbow soup, which might also be a delicious form of soup. Okay, finally, JT, thank you so much for being here. What do you think is at the end of a rainbow?
Well, since a rainbow is a circle, there is no end.
I like that. Oh, and we have a really cool picture here that I forgot that I wanted to show you, because as JT was talking about, it's all about angles, and that means that a circle, a rainbow would be a full circle. And if you go up in a plane during the right conditions, you can look down and you can see a full circle rainbow. It's very faint at the bottom right here, but in the right conditions in a plane, up high above during a rainstorm. So I don't know, the safety of this, questionable. But you could see a full circle rainbow, which might be the rarest thing of all. JT, thank you for joining us again on the ROMKids Show.
You're welcome. Thanks for having me. It's fun as always.
This was great. I learned a lot more math than I expected. The coolest thing is how a star in the sky is light from the past, that the sun itself, when we see that light, is from 8 minutes ago, and a great way to remember all the different colors in the visual light spectrum is Roy G. Biv. Next week on the show, we're talking all about weather. I know some in our audience are very excited for this one. We're going to talk about rain, storms, tornadoes, maybe even the rain cycle. So lots and lots of really cool things next week on the show. If you're watching on YouTube, hello to all our friends there. And thank you to everyone who joined us live. In 2 weeks' time, Dr. Santiago Claremont joins us to talk about why birds fly and how birds fly. So lots of real awesome stuff coming up on the ROMKids Show. Julie Tomé and I say thank you. Wear a mask. We love you. Stay safe. And see you next time. Bye, friends.